with fixed earth support method. Okay, so let's start. So this is a numerical problem. So this this is the seat pile wall, which is anchored with an anchored rod and with some small mass which is anchored bulkhead. So the fixed earth support system analysis is used when the seat pile wall depth is deep. Okay, and this is the deflected shape of the seat pile wall. Okay. So if we compare it with the cantilever seat pile wall, the cantilever seat pile wall derives its strength from the is- passive strength of the soil below the dredge level. Here it is anchored also. So for anchored bulkhead, the strength of the soil comes from the passive resistance below the dredge level and also from this uh, anchoring anch- from the anchorage. So the soil properties are given. So this from the top of the backfill to the location of the anchor rod, Z equals to 1 meter is given. The water table is given. H1 as 3 meter. Just below the water table up to dredge level is given 6 meters. So the effective height is 9 meters. So we have to find out this embedment depth. This J is the point of contraflexure. Okay. So the numerical reads out calculate depth of embedment of the seat pile wall and the pull in the anchor rod for the anchored bulkhead system. So first discuss there are few assumptions involved. So what is the difference between fixed earth support analysis and the free earth support analysis? So first, as the seat pile wall depth is more, we generally go for fixed earth support analysis. When the seat pile wall is short, we go for free earth support method analysis. So the inherent assumption in this is this seat pile, this A, top portion and the bottom portion of the seat pile B, this AB. This AB, we assume it as a elastic beam and it is simply supported at D and it is fixed at B. The earth pressure distribution is shown in the respective figure. So just notice it. When we use the fixed earth support analysis, this is the bending moment diagram and this is the deflected shape. Just follow the cursor of the mouse. This bending moment diagram is like that. For the case of seat anchored bulkhead seat pile wall design, so you can notice that the bending moment changes sign here. So this J becomes the point of contraflexure. This blue which I have shown, this is this if the seat pile wall depth is small, then the bending moment diagram for uh, anchored bulkhead seat pile wall with a shallow depth, it is like that, goes like that. So the point of inflection is less in that case. Okay, so the density above the water table is given 1.9 ton per meter cube. The density below submerged is given 1.0 10 per meter cube. Soil is 5 equals to 30 degree. So it's a sandy deposit. So up to water table, this is the active pressure distribution. At dredge level, this is the active pressure distribution, the effective active pressure PA, which acts and the distance between the location of the anchor rod is Y1 bar. This is the passive resistance. The effective passive resistance act as a distance of Y2 bar from the location of the anchored rod. And from the dredge level to the point of contraflexure, the distance is Y0. Okay, so let's start to solve the problem. So the first thing is how we do the fixed earth support analysis. So this is the diagram. This is the active pressure distribution. This is the passive pressure distribution. And this is the deflected shape of the seat pile. So because it is anchored and with a small mass, so it is known as anchored bulkhead. So this is the simplified earth pressure diagram. So in this, this whole length of the seat pile wall AB. This AB is we idealize it as a summation of AJ plus JB. So what we do? So this is active pressure distribution. It is a passive pressure distribution. So at the point of J, which is the point of contraflexure, where the you have seen bending moment have changed sign. So the we draw it the active pressure distribution up to the depth Z. So this is at the water table. Then we proceeded it and drawn up to the depth of H plus Y0. So this is the active pressure distribution. This is the passive pressure distribution, and whatever this distance GB, we actually replace it by a shear. So it is also written GB is replaced by RJ. RJ is what? RJ is a shear force. So to discuss just again, this A point is the top of the backfill. D point, this D point is the anchor rod label. E is the dredge label. J is the point of contraflexure where the bending moment changes sign. B is the bottom of the seat pile wall, and the total height is this water table. So this is H1 water table from the top, then water table to dredge level S2, so H. Okay, so now the question is in previously when we have seen the cantilever seat pile wall, this Y0 we calculated by equating the passive resistance and the active resistance. Okay, and from that expression we could able to calculate it the Y0. But in case of fixed earth support analysis, this Y0 depth, this Y0 depth dependent upon the relative density, means how what is the compactness of the soil at that stage. So it changes with the internal friction angle. When it is 20 degree, it is like 0.25 H. So H is what? This H1 plus H2 up to dredge level, the height of the sheet pile wall, resisting the backfill. For 30 degree, it's 0.08 H. For 40 degree, it's 0.007 H. So for the case 30 degree is given, so it comes out to be 0.08 into 9, so 0.72. Okay. So we have broken the analysis of AB into AJ, and then from J to B. So this is the shear force. So the effective uh, shear force in opposite terms RJ, and this is the triangular distribution. This is the rectangular distribution there, and then the we have not shown the deflected shape starting from the bottom, but rather than at point F. So the passive resistance generated by this FB. So we replace it by a effective force of say uh, by a concentrated load RB at the location B. Okay. So now we will proceed. So first thing is suppose a re- suppose a seat pile wall is retaining some backfill. So if the wall goes away from the soil, we call it as an active pressure. If it goes, the seat pile wall goes towards the backfill. It is known as passive case. So we know that active pressure coefficient K equals to 10 square 45 degree minus 5 by 2. 5 is 30, so it comes out to be 1 by 3rd, where Kp is calculated as 10 square 45 degree plus 5 by 2. So Kp comes out to be 3. So at the water table, this is the pressure distribution triangular. Then this becomes overward to bottom layer up to the depth of this is H1, this is H2 plus Y0, because this is the point of contraflexure. So it comes out to be this calculation of this the area of the triangular diagram, rectangular and another triangular. So the total active pressure comes out to be summation of these three. So first calculate this one. One is what? One is a half BH. So half B. So base phase, this is the stress uh, K, K gamma 1, or height is H1. Then the rectangular variation K gamma H1, this is the stress. Then it is occurring at, so this triangular variation acts as a overburden, so it becomes at the stress is K gamma H1, and it's act as a height of S2 plus Y0 because this is point J and this is the dredge level point. Okay, so this is S2 plus Y0. Then the third diagram, this third triangular area, so it becomes half BH. So half Ka gamma dash and it act as a point at S2 plus Y0. Okay, uh, into this height. So this is S2 plus Y0. Okay, so we can calculate these things and it comes out to be 23.15 ton per meter. Okay, per meter length of the wall. Now we can also calculate the passive resistance. So we can see this passive resistance. Okay, so active we have calculated water table. Then at uh, the level of the point of contraflexure, now we will calculate the passive pressure. So what is the passive pressure? So passive pressure, it is a triangular area of this triangular diagram. So it will become a half Kp into gamma dash. Why gamma dash? Because it is sum is there. Okay. So this area is half base. So Kp gamma dash into y0 and the height is y0. So it comes out to be 0.78 ton per meter. So we have done the calculation of active pressure and passive pressure uh, at the point of location of contraflexure, which is point J. Now we will move further. Now this is the final pressure diagram. This whole analysis of this AB from the top of the backfill to the bottom of the seat pile wall. So this whole depth. Okay. So the whole depth analysis broken into AJ plus GB. So we can do the equilibrium of the moment of forces about this anchor rod at a depth Z from the top. So what it is? So this shear force RJ, this shear force RJ acting as at a distance. This is this whole length is H, this is Z, and this is Y0. So RJ is acting at H minus Z plus Y0. So it's a Y0 plus H minus Z. So this is the distance RJ from this point of location D. Then what are the other forces? Now active pressure, thrust is acting, passive force is there. So we can calculate this. We have earlier calculated PA1 acting at what distance. So it's from this, it's a 2 by 3 of this height. So this height is whole height is H plus Y0, then minus H. Then comes the passive force. So passive force is this is H plus Z minus 2 by 3 of Y0 because it H is so 2 by 3 of Y0 plus H minus Z. So we just by putting a respected value of y0 because y0 have earlier depended upon the relative density for phi 30 degree it's 0.08 h we have calculated 0.72. Then comes h we know, z is given, pa1 already calculated, passive pressure is already calculated. We are able to calculate this shear. Okay, by removing the this GB. So what is the shear coming at the point of contraflex? Okay. So now what in the numerical problem it is being asked that what is the axial pull by the anchor rod. So it is active pressure minus passive pressure minus this shear force. So it's 23.15 minus 0.78 minus 13.78. So it comes out to be 8.5 ton. Okay. Now we have to find this depth. So below the dredge level, what is the depth? So this is known as embedment depth. So we need to find out. So how we will going to find out? This is moment of forces about this anchor rod location. So from the top, jet depth below. Now we will take the moment of forces about base. So then we are able to find this d distance. This is y0 and this is overall d. So this become d minus y0. So we will take about this look. So now we will find the moment of forces on a span GB about this base of the seat pile wall. So this becomes RJ into d minus y0, because this is the lever arm, this is the shear force. So rj into d minus y0, and and then these two are the, this is the triangular component earth pressure, and this just this rectangular component. So this is, uh, as we can see earlier, it is a effective passive minus active, as shown in this figure. Okay, so active pressure is also acting, passive is also acting. So one for the triangular pattern and second for the rectangular pattern. So it comes out to be half kp minus k gamma submerged, because it is below water table, d minus y0. So this is the lever arm into the centroid x at 1 by third of this height. So d minus y0 by 3. And now for this rectangular, the stresses. These stresses is passive force is acting, active force is acting. So it is kp minus k y0 into gamma submerged, because it is below water table. And the above pressure is up to water table, Ka H1 gamma dry unit weight plus Ka this below water table H2 uh, uh, gamma dash, okay, into the lever arm distance is d minus y0, and the centroid acts this lever arm by half, so it is d minus y0. So we have earlier calculated the shear force Rj as 13.78, Kp, Ka, Y0, all we know, so we can put it and find out the embedment depth. And this embedment depth is a very important parameter in the design of anchored bulkhead or anchored seat pile wall. And this also govern the overall stability of the anchored bulkhead, and very important in the economics and stability of the project. I hope you understand. If you have any doubt, you can ask. Okay.